Hey everybody, sorry I couldn't be there today. I just wanted to make sure though that we didn't have a relaxing day, haha. So I wanted to make this screencast for it to be played in class. So what we're going to do is answer that question that's on the top of the screen to try and incorporate what we've been learning about vectors in a real physics type way. Specifically today we're going to focus on the velocity vectors of a ball that's rolling horizontally off a cliff. But to do that, I want to give you a little bit of background. So, when we have this ball rolling up the top of a cliff, we're going to first just turn off gravity. When we turn off gravity, we're going to give this ball just a small 2 meter per second horizontal velocity. So we're going to turn off gravity. So 1 second later, the ball is going to be right here. It's still going to have a horizontal speed of 2 meters per second because it's not accelerating horizontally. 1 second after that, again, 2 meters per second. Always 2 meters per second. 1 second later, and the ball's not really getting smaller, just easier to draw smaller. Still 2 meters per second, and one more time, still 2 meters per second. So each of these distances, these are 1 second intervals, from here to here takes 1 second, here to here, etc. So each of these would be 2 meters. I don't want to draw it because then I have to erase it. So from here to here is 2 meters, from here to here 2 meters, here to here 2 meters. So in the time, from here, time equals 0, to time 1, 2, 3 seconds, and 4 seconds, the ball would have gone 2 meters, 4 meters, 6, 8 total meters. Or distance equals v times t. Our v is 2, our t is 4. There's our 8 meters right there. Okay, so our ball is moving horizontally, gravity had been turned off, and it's happy as could be. Well, now we're going to forget the horizontal piece, forget these 2 meters per second, just for a second, and look only what would happen if the ball were right here to begin with and dropped straight down. Well, doing it over on this side, our VI is 0. So 1 second after that, we're going to have VF equals 0 plus A times T. And for this purpose, we're just going to round A, and thus G, to negative 10 meters per second squared. It just makes the math a little easier. That's meters per second squared. Makes the math a little easier, so our V at each individual time is going to be negative 10, that negative just meaning direction going down, times whatever time we're looking at. So 1 second later, it's going to be moving at 10 meters per second, so it'll fall into roughly here at 10 meters per second. So something, trying to get it to order about there, 10 meters per second. And then 1 second after that, the ball was initially going a little fast already, so it's going to have traveled a further distance. So it's not just going to be this, it's going to be actually maybe down here. Going, not 10, sorry, 20 meters per second south, down. So negative 20 meters per second. Negative 10 here, 0, negative 10, negative 20 meters per second. And for 3 seconds, it's going to be way down here, probably even further off the screen almost, at negative 30 meters per second. So the ball with gravity off is just going horizontally, 2 meters per second each time. The ball, should make this arrow longer. The ball, when it's falling, starts at 0, so there's no initial velocity here. 1 second afterwards, it's going 10 meters per second towards the ground. That's at negative. 1 second later after that, negative 20 meters per second towards the ground. Then negative 30, negative 40, for however long it's falling. Again, assuming that G is negative 10, just to make the math easier. Well, this is really what's happening when a ball is rolling off a cliff. It's moving horizontally, nothing's slowing it down, and it's also falling due to gravity. The thing to remember is gravity doesn't care whether the ball is rolling side to side or not. If you ever watch those cartoons where Wile E. Coyote is running off the cliff, and then he sort of pauses until he looks down and realizes he's off the cliff, and then a couple seconds later he falls. That's not really what happens in real life. As soon as you have that ground taken away from you, it's gone, and you start falling. Same thing that would happen to this ball. So we did the horizontal piece, we did this vertical piece. The simple combination allows us to see what happens when you really have a ball moving in true pattern. So horizontally, 1 second after it leaves the cliff, our time 1 second really is the time after it leaves the cliff. 1 second later, the ball horizontally is here, but vertically it's here. So truly, it's a combination of the both with a 2 meters per second horizontal and a 10 meters per second down. Well, these are two just components. So we don't really want this here. We want it here because it's tip to tail. And I don't have to write the negative really. I'm kind of being redundant if I do because I have the arrow pointing down towards the ground. So that takes care of my negative now. So I got 10 meters per second, 2 meters per second. Well, my resultant, try to make it thicker. My resultant vector is this. And then next second later, the ball horizontally is here, but vertically is here. Horizontally, it's still moving 2 meters per second. That hasn't changed. But vertically now, it's moving way faster at 20 meters per second. Again, tip to tail really has to be here. Get rid of this one. And our resultant is that guy. And then 3 seconds later, vertically, it's here, horizontally here, vertically here. So the ball, this one's not drawn very nicely to scale. Goes way off, you can't even see it. So what happens is, all of these resultants are nice velocity vectors. You have 2 and 20, 2 and 10. You can find the resultants. So 10 squared plus 2 squared would be 104, square root of 104, whatever that speed is. You can take out your calculator and do 104. And we can also find the angle. Angle would be, for this vector, inverse tangent. This is our angle right here, because that was our first vector. Here's our hypotenuse. So our inverse tangent would be 10 over 2. So in your calculator, inverse tangent of 10 over 2 would be inverse tangent of 5. Whatever that angle comes out to be, it'll be the angle, and that would be, in this case, you could say south of east. Really, it's like towards the ground of east. A little harder to say. But you could just have your angle. Same thing here. It would be 20 squared is 400, 2 squared is 4, so it would be square root of 404 would be our V. And our angle would be the inverse tangent of 20 over 2. Same thing, that's your angle. And we can get individual pieces of information about our path. Over here, our only velocity is 2. There is no vertical piece, so there's no vertical up or down component. But what's cool is, if you look at this, you really get a cool way of viewing and seeing how this motion comes about. So without moving my pen, or without moving my, without removing the ink, sorry, I'm going to just sort of trace out the motion of the ball. Well, it's coming out this way, goes here, it's going to start falling, hits this one at that angle, perfectly in line with this resultant, keeps going, and maybe I drew this one too far, and it's getting steeper and steeper. But we understand that. Ooh, I love it. When we go throw something off a cliff or throw something just sideways, we know that it does kind of this. It doesn't just go out and then fall. It doesn't go perfectly diagonal. It kind of droops in a big arc motion. So just get rid of some of this. Sorry. Yeah, we'll just clear it off. Forget that. So the motion that it goes through is in a big arc. But what we really need to do is look at it and break it apart into horizontal pieces and vertical pieces. And in the next video, coming right up after this one, we're going to show you how to do that and then look at a problem more specifically in which we have horizontal and vertical pieces, and then you'll have a worksheet. So this is the first video. You should have taken notes up to here. Should have tried to copy this drawing down as best you can. I understand that it's a little tricky and very complicated, but if you need the sub to pause it for any moment of time to get this picture down where you have the horizontal pieces going evenly spaced, not changing, you have the vertical pieces getting further apart with changing speeds as they're getting faster and faster every second, and then we kind of combine them. This 2 seconds correlates. You meet them in the middle, do your resultant vector. You can quickly find the speed and the direction. For both of these, we have the third one over here, which just out of range. So we can see that. So in the next video, which is coming right up, you will see how to do a problem with a ball rolling horizontally off a cliff. Thank you.